Get going here. It's terrific to be with folks for another session discussing what I consider a quite extraordinary paper and contribution from our colleagues in Florida. This paper towards the unified theory of time-varying data. And we started talking about the paper last time and talked about some of its basics. But I wanted to expand on that this time, and specifically some of the sections that I asked us to go through for this time, which is sections 2.3 and 2.4 of the paper. This is one of the most significant papers I've read in terms of I think its potential for applied category theory more generally and for our work in particular. And I therefore think it merits the three sections which we're devoting to it, sessions we're devoting to it in the course. So before going into these particular sections, 2.3 and 2.4, in more detail, I'll sort of remind us of set the context here in terms of some of the basics. So we saw that this paper uses Grothendieck topologies formulated around categories of intervals where the objects are intervals and the morphisms are these inclusions of one interval into another. These sort of inclusions where 1, 2 is inside 1, 3, 2, 3 is inside 1, 3. And down here at the lowest level, we have a set of these kind of what might be called rump or degenerate intervals, which start and end at the same time point, but are closed. So these are termed snapshots here. And importantly, there needs to be a notion of coverage that's brought forward for such a category of intervals. And they use what's termed Johnstone coverage, which is coverage of an interval from a start time to a finish time, is given by any pair going from the start time to some intermediate point, from that intermediate point to the finish time. This is a thin category, it's a poset, and the join of any two intervals here just goes from the minimum of the start of them to the maximum of the finish of them. I will note, moreover, that it's what's called a join semilattice, so it has all joins for all intervals. Okay, now with respect to this Grothendieck category, Grothendieck topology on that category, with this notion of coverage, the paper examines sheaves and co-sheaves, which map from T-op for sheaves, or T for co-sheaves, to a data category. And they require just that the data category has pullbacks. And you may recall that pullbacks can serve, for example, at set to characterize intersections. fact, at growth and topologies, that's kind of a motivator for some of the intuitions with them. But here, pullbacks have to exist in this data category for sheaves, and pushouts have to exist here in this data category for co-sheaves. Now, this mapping, if it's from T-op, it is of necessity, by definition, contravariant mapping, right? So each of these intervals here within our interval topology gets turned into, or it gets mapped into some possible data over that interval, right? This is describes the stalk over that interval, stalk, S-T-A-L-K, in a sheaf theoretic sense. And that's true at all levels here. But the morphisms here, these inclusion morphisms, get turned into restriction maps here, right? And with this category on the left being a preorder with these intervals and inclusions, we have lots of commuting squares. It's a thin category, and it by nature it commutes. And if we map it over, we get, because functoriality honors composition, we get commuting squares here. And we are looking for for F here to honor limits, and that means mapping this co-limit in T into a limit here, where you'll recall that one of the definitions of a key component of having a definition of the limit is it's the unique object or the unique cone such that all other similar cones factor through it, such that all of these paths here have to commute, all of these paths underneath here. And we need, by virtue of this being a sheaf, that this F of this limit is the limit of the F. So we do want, you may recall the co-equalizer, the sheaf here for this, to have a data assignment that basically is a monomorphism into, so it's a subset of the products of these different substocks, constrained so that they equal each other. In other words, the pullback associated with these. And so we talked about that last time, that sheaves are associated with this limit structure, and the limit structure can be seen in the definition of a pullback, in the sense that we want not only any assignment of data here and any old assignment of data here, not just the product of those, but the products of those that match up on all overlapping regions. So if this one goes from 1 to 3, this one goes from 2 to 4, the regions between 2 and 3 need to match up, right? They need to give consistent pictures just as much as if you're looking for, you want not just all pairs of shirts and pants, but shirts and pants of the same color, to use Eugenia Cheng's example. Here, we want not just all products of this and this, to be reflected in our data here, but all products of this and this that agree on their overlap. Those are the ones that we want this limit to be a subset of those products. So here with sheaf, it bears noting that we get these consistency requirements at these different levels. But one thing I emphasized last time, and I want to emphasize again, is that the bottom level here, including this bottom set of snapshots and this first level above that, there are no possibilities of taking pullbacks to inform this, to sort of take these and put it there. Instead, what we have is a characterization of data here from our domain. And what happens is it gets pulled back to these upper levels so that whatever's assigned to these upper levels, these broader intervals, is consistent with what we see down here for these snapshots and these maps between the snapshots. And we saw last time that for sheaves, these are spans. And spans can characterize relations, for example, between this and this, or partial maps of this, or indeed functions from this to this, as sort of different variants of more constraints on spans or full spans. And so when we specify these lower two levels, we're doing so from data that we have. And these deductions which are in place for higher levels reflect that data and make use of it. An important point is that the pullbacks need to be the same. This is key, regardless of our intermediate point P. So if we consider, you remember this idea of we have Johnstone coverage for a given interval, say 1 to 4. That Johnstone coverage means we can consider it covered with an interval from 1 to P and P to 4, reflecting the start is 1 and the finish is 4. But we need this pullback to be the same as part of the conditions associated with the sheaf, to be the same regardless of P. So regardless of whether we break the data up into 1 and 2, and then 2 and 4 here, or whether we break it up into 1 and 3, and 3 and 4, we need to get the same pullback up here to this top level row. And the same thing is true for these sub areas. So these restrictions need to agree, and we need to get the same value. For co-sheaves, we have a similar picture, except now we're dealing with pushouts up here. And if we have overlap, we glue together around that overlap. We identify around that overlap for areas of overlap. And the sense you get here is accumulation. Here we had a sense of constraining for a consistent picture, winnowing down our understanding of what's going on in the sub areas so that they're consistent. Here, what we get the sense of is accumulation. We're taking what's going on down here at the lower levels, and we are accumulating it up to give a consistent picture of everything that's gone on across here, but not double counting when we have overlap, not adding something in twice just because we saw it as part of for example, 1, 3 here and 2, 4 here, the interval from 2 to 3, we don't double count what was going on there. We just include it in our account by identifying it. So here, these are pushbacks, and all of these pushbacks need to be consistent in a similar way to here. No matter where we break up our time from 1 to 2 and 2 to 4, or from 1 to 3 and 3 to 4, we have to get a consistent picture up here for it to be a co-sheet, a valid co-sheet. So the terms that are introduced early in the paper, but especially in the sections we read for today, associated with this are, with the pullbacks, we're getting a persistence perspective. We're requiring things to be up here, to be in each sub-interval, so that no matter where we break it up in time, that we get a consistent picture of what's up here. We're constraining things going up, and we're requiring it to be there in each and every interval to make it up to the top. By contrast, here, we get a cumulation perspective, a cumulative perspective. If it's in any sub-interval, we count it. We're just extra sure not to double count it. Okay. So within the readings, so I guess the basic understanding of persistence was something we talked about last time, and I'm not going to dwell on it, but I'd refer you to this, fragment from the paper, as well as the text here, and similar for accumulation. I did want to make note of one or 2 points. So there's these very nice diagrams from the paper, and I need to add this attribution here and here as well. But there are these very nice diagrams showing like the persistent narrative, in this case for graphs, right? So here are snapshots over time, right? These are the data we're given. And they're in the form of graphs. And we started talking last time about this key point emphasized in the reading for today, that by treating data category D as a category of C-sets, we can represent a vast and useful array of structures and be guaranteed to push outs and pullbacks for all of them, because such C-sets are associated with topoi, amongst other things. So here's the data we're given in the form of graphs at these snapshots. Here's some data at the level above that characterizes the sort of mappings from this to this, this to this. And the persistent perspective here is one of retaining just those things that are present in the graph at all points, which in this case are merely the vertices. A, B, C, D are present throughout. There is no one edge that is present throughout, not B, C, because it's here. It's also in this snapshot, but it's not here. Not A, B, because whilst that's here, it's not in either of these 2 snapshots. Not BD, because that's not here, even though it is here. You'll notice that for subintervals, like this interval here, there is a BD and AC in each one, and so they're reflected here. But they didn't make it up to this level because they're not in this picture. And remember, to make it here, it has to be here. It has to be here through all subintervals. By contrast, the cumulative narrative here is quite different, right? It's accumulative, as its name would suggest. So if we have a link in any one of these, say AB, it's only present in this first. It's not even present in the second and not in the third. But AB makes it up here. Similarly, CD makes it up here, even though it's only on this one. BD, even though it's not in this one, makes it up here. But what's notable, and there's actually a somewhat parenthetical remark in the paper, just a sentence or two. But you'll notice that some edges here, BC, the edge between BC, is present twice. It's present twice because it's present once, it disappears for an interval, and it's present again. It's therefore two different intervals or two different connections from B to C is the idea. And hence it makes it up here twice. You could see there's two edges going between B and C. One from here, one from here, and by extension, they're inherited here and here. It's notable that my understanding is if there were a structure, and unfortunately there's not one here to showcase it, but if, for example, BD was present in all, were present at all, there'd only be one edge BD here because it's present continuously throughout that time period. The fact that there's an interruption means it's actually added more than once to the cumulative narrative. We consider it a different kind of instance, as it were, of BC. Okay. Now, working towards zeroing in on sections 2.3 and 2.4, I'll just note here that, first of all, persistent narratives and cumulative narratives form a category. And as I understand it from the definition, it's a little bit reading between the lines here. This is for a given temporal category, given Grothendieck topology for the temporal category involving intervals and inclusions, and a given D, category D. Each of these constitutes PE, so persistence from temporal, the temporal category to the data category D, and cumulative from temporal to D. They are categories of temporal sheaves. And we have objects here that are sheaves or co-sheaves, respectively. You'll notice I'm writing this in the form that's common in math, like for when you have dual things, just for brevity, you say like persistent category PE from T to D, or respectively cumulative from T to D, these narrative categories, you say respectively to mean for the dual. And then every time you mention it said like sheaves, you just say respectively co-sheaves to indicate what it is for the dual. Pull back, respectively, push out for the dual. So that you don't have to re-explain it twice or re-explain it. So here for a given T and a given D, we have these categories of narratives. So I think what we'd have here is something like the following. We'd have something like a category like this, and we'd have various objects here, which are different these are different persistence narratives that abide by this persistent narrative condition that we saw a few minutes ago here. So for this persistent narrative. So it has to have this invariance property as to where it's divided up. And then we have these morphisms here, which might be sheaf morphisms, which would be sheaf morphisms. And that would map from one the same interval category to another for the same data and same data category for each. And those might involve some, I'm thinking about it, but I suspect they might involve, like if these were categories where D were graphs, you might have a mapping from this one here to this one here, which involved a sort of coarse graining of this graph in this other one. Or maybe you have a persistent narrative here about a small area of the graph, and then you have a persistence narrative here about the bigger graph, and this is some inclusion. So everything that goes on here is reflected here, for example. So you might, like maybe this is just a subpiece of a much larger graph that evolves A through Z. And this is just a piece of it. And you might have the same temporal time frame, time horizon, same data category graphs, but you would have this natural transformation. Much as you do behind pre-sheaves, you would have a natural transformation here that would map all these into as inclusions into a larger structure. So something along those lines. So what I've just drawn there might be PE of this T comma D. And we have a massive number of possibilities here, but they're related to one another, and some may have no natural relationship with one another. And then we have a similar one for cumulative narratives. Okay, now I want to make sure that I'm right. So one point that ends up being rather helpful for this cumulative and persistent perspective to capture it first, I think, is to talk about change of base functors. So what we saw here was all for fixed T and fixed D. And that's interesting. But one of the more useful things is to think about cases where we have a change in data from one type of data to another. So maybe we have data on graphs, persistence narrative on graphs, and we want to turn it into data on a set, the set of edges for those graphs. So if we have a functor for a given graph, extracting its a set of edges for that graph. It's a forgetful functor, just extracts a set of edges. That allows us to then take a narrative for a given temporal category in graphs, something along these lines, say a persistence narrative for a temporal category mapping to graphs. Here we go. And we can turn it into a persistence narrative on sets of edges for this graph, for example. So this persistence narrative on graphs could be mapped canonically into a persistence narrative on sets, where each of these graphs, you could just imagine it, right? My goodness, how can I not do this? So mapping persistence narrative. Maybe I'll do cumulative narrative if you don't. Cumulative narrative on graphs to cumulative narrative on set. Okay. So this is what we're going to do. We're going to imagine we have this functor F. Go. actually, you have a functor K is what's, I think, called for here. Yeah, K from C to D. So I'm going to do K going from graph to set. And this extracts edges from graph. This is a forgetful functor. And that's of interest in the sense of adjunctions. Okay. So if we have a little graph, here's our graph with A, B, and C. And yeah, sure. We'll have one from B to B, and we'll have one from A to C. So here we have F, G, H. We'll call this J. And those are just edges. So you may remember we could encode this as a pre-sheaf. Remember the schema for graphs. The schema category looks like this, right? Well, we have source, target, right? So the instance of this represented by this just has edges. What is the set of edges here? Who could tell me? What is it? Yeah, exactly. So I'll actually draw this over into set. This is just encoding this, right? So this is going to be in set. This is going to be in GRPH. Goes by different names. Sometimes it's GR, I think. Okay. So A. Okay. So F G. I made a poor choice there. So I should put it over here. Okay. Okay. And so F, G, H, and J. Okay. Good. V maps over here into A, B, C, right? And then we have the source and target, which I'm not going to write out. Source of F, target of F of C, etc. Okay. Now, this is sort of an object in graph. In the category of graphs, it's just some object. It just happens we could encode it. Think of it being encoded that way. And if we map that to set, this is going to map into the category set. So this is going to be one of many objects in the category graph. Here we are, graph. There's a bunch of objects here of this sort, and this is one of them, right? This is one of them. Skies, say that one. But there's all these others. And now we have K mapping from this to set. And that particular graph is going to be mapped over into exactly this set. F, G, H, J here. Just going to be mapped into that. And this is this forgetful functor K, right? And I'm going to make it a bigger map. Here we are. So K is going to map all these others, but we're not going to concern ourselves because those aren't our examples. It's going to map all these others to various things over here, right? Whatever. Okay. Okay. So we have this nice functor, and we are going to now consider that we have a cumulative category. So we're going to have a cumulative category from some temporal category T to a temporal category D. And this itself is a functor covariant from T to D. Persistence would involve an op here, right? For persistent mapping, it would be there. But this is in this category. This is our category where all the objects are these persistence narratives. And each of those persistence narratives is one of these special functors that abides by these extra rules associated with, okay, where is it? Where's our persistent one? Or where's our cumulative one? Okay, well, you know what, I could just show it here. It's with this cumulative condition, right? So here, each of these ones in this category is of that form. Because I drew it in blue, and the other one I'll draw them in blue here. So this is our cumulative category with the nice red arrows. Okay. So each of these is a narrative, a cumulative narrative. Okay. Now, they're a cumulative narrative with respect to graph. So we're going to specifically have this be, for our case, we will have it be, we're going to specifically use D equals, for us, D is going to be equal to graph. Great. So all of these are describing temporal graph narratives, just like cumulative temporal graph narratives, just like we have here, right? Just like this. Okay. Each of these involves that from a common category T, temporal category T. They all involve these structures. And what this change of base idea is saying is now we have one of these things. We have one of these K's here. One of these K's. And these K's are going to map over from this to a category here, where we're going to have, so this is going to be on the left here, CT, comma, not just D, but graph, specifically for graph. That's our graph narratives. And each of those is going to be mapped now with this, by combination with this K. That's right. It's actually not just K, I'm sorry. It's K combined with F in a certain way. There's going to be a mapping. It's going to involve K, but it's not going to be K itself. Here we go. Okay. So it's going to look like that. And I think I'm just going to draw it for each of these guys. So that's going to go there. That's going to go there. That's going to go there. And what are these things over here to the right? What are these things being mapped? Well, what we have to the right here is cumulative T, comma, set. It's this idea of set here. It's this idea of set here, in the sense of these are going to be, I don't know if I should make them the same. Sure, but they're cumulative narratives involving set now. So I'll put these here. They're a cumulative narrative here, but involving set. So each of these guys is transported there. And how does that work? Well, it works in exactly this means here. So look, if we have a cumulative narrative from cumulative of C to cumulative, or to get a cumulative narrative of this sort, all we need is, first of all, one of these guys. This is a map from T to graph. That's what this is. So this is T to graph, right? That's our F here. So we have T to graph. That's what we have. Great. And we're going to take that. I'm going to take each one of these. That's what these are. Each of these is a temporal narrative, temporal narrative, cumulative temporal narrative. Each of these involves one of these things, right? Cumulative narratives. We're going to take each of those in here, and we're going to turn it into one of these. How are we going to do that? Well, we have something that maps from T to C, right? So maybe I'll have a little pointer here. This is some particular map from T to graph, right? Some particular temporal narrative. Some particular functor of this sort. Like this one here. That would be just one dot here. And what we can do is, and let's give this one a name. Let's give it a name, if we could. This is a particular one. We'll call it, what do we call it? Maybe we'll call it X. X is this. That's what this cumulative narrative is. Okay, it's our X. We're going to map it over into something from C to set. There we go. Sorry, from T to, this is something here from T to set. These are cumulative narratives from T to set. our temporal category with all those time divisions and so on, all that lattice of divisions. We're mapping it we're mapping each object of that into a set. And we're mapping all the inclusions from this into these set related functions. And this has the special property of observing that sheaf condition. Okay. How do we get this? Well, this is given in a certain way. It's given by, first we're going to map to X, and then we're going to map with K. Right? X is going to take us for any T, any interval in the temporal category, for example, any object in the temporal category. It's going to map to a graph. And K is going to map that graph into our set. It's going to map it into a set. So here, F is this X here. Maybe I should have called that F. Maybe I should have called that F. Yeah, just so people are less concerned or less confused by that. I'm gonna make this smaller. And oh, come on. Okay, come on. Why won't we be a small eraser? Oh, come on. Be a small eraser. Okay. Come on. Oh. Okay. Living on the edge. Okay. Fine. So this is going to be F. That's right. That's right. So this is a category of narratives. Category of narratives. Each narrative objects here are narratives. So these objects are narratives of this form T to D. So objects are temporal sheaves or co-sheaves here. There's their co-sheaves. Okay. So all we do is we post-compose by K. So given one of these, we can turn it in, given a mapping like this, we can turn it into a mapping on sets. And what would that mapping look like? Well, let's do it out for this. What? Zotero. Okay. Let's go copy it in there. Let's go see if we can give this thing a run for its money. Okay, so this is going to be particular cumulative mapping of cumulative narrative on graphs. Okay, let's go see. Okay, it looks like it's not going to cooperate. Okay, so it's not going to put it in there directly. What I'll do is take it directly from. Is it in here? Is it? Yes, here it is. Okay, Okay, and let's zoom in. And let's take this and save it. And now we'll go put it in our here. We're gonna insert an image. There we go. Okay. So what I'm claiming is that if we know how to turn each graph into a set, we can take this and turn it into a narrative on set, right? A cumulative narrative on set. That's the bold claim here, right? So here's our cumulative narrative. Okay, no, sorry, I need to select this, not, okay. Well, I could always reinsert it. That's a good point. Let me reinsert it. It'll be finicky. So there is our cumulative narrative on graph. What we're going to do is we're going to fill it in for what the cumulative narrative on set will be. So that's the cumulative narrative on graphs. We'll fill it in to be a cumulative narrative on set. So you'll tell me what's going on here. What I'm going to do is I'd like to erase this. I may have to just put, I guess I could put squares, hidden sort of white squares over it. Maybe that's the least bad thing to do. But maybe we'll just write on it for now in the interest of time. Okay, so I'm telling you, we have this nice functor that can map from any set from any graph to set. So what's going to be the set that's extracted from this? Well, we can write them in kind of simplex form. It's extracting the edges, so we can write the edges in oh, sorry, I'm in the wrong application. There we go. No, I'm confused. I thought I pasted this twice. Am I confused? Yes, I have it twice. Okay, here we go. Come on, get back there. Okay. Okay, so what's the set of edges here? Yeah, I'll just write them like this, BC. We're gonna get into some issues up there. We'll have to subscript from them. So BC, keep on going. AD, BA, and what? CD. Good. Good. Okay, what are the edges here? BD and AC. Good. What are the edges here? BD, AC, BC, and what? AD. Good. Okay, what are the edges up here?
BC,
Okay, BC,
AD,
AD, BD, AC. Okay, edges here. BC, AD, BA, CD, AC, BD. Okay, how about up here?
All the ones from before plus
Good.
BC and extra BD.
Okay, good. Yeah, so it's basically the same as this with these extras. So I'll do BC1, BC1, BC2, and then AD1, AD2. You know, in terms of this, I think actually it might be easiest to just do it in LaTeX mode. So I'm going to say BC1, BC1. We'll put it like this. BC1, BC2, AD1, AD2, and then BA or AB, I guess. BA, thanks. BA. Oh, sorry. This somehow got BA, CD, AC, and BD. Okay, so why is this not? What did I do wrong? Looks fine to me, but let's I don't see anything wrong with it. Let's see. No. Did I? Ooh, that's fine. Okay. Something is a little bit off. Okay. I'm just gonna put it like that for now. And what we're claiming is that this is actually a cumulative narrative. That anything mentioned down here makes its way up here, and that if something was here once, something was here twice, it'll be listed up here separately, for example. I think you can convince yourself that this is a cumulative narrative, that it's all consistent. Because indeed, we have structure preserving mappings here. Structure preserving mappings of this form that can extract them. And these mappings here, we're honoring the structure associated with this. All we're doing is post-composing. And the same thing can be done with persistent narratives. So in short, if we have a cumulative narrative from T to C, we can convert it over to a cumulative narrative from C to D if we have a functor from C to D. And similarly for persistent narratives. Now, what's interesting, and I think part of the fascinating components of this paper, many fascinating components, is that if you have a continuous functor, and you'll notice that there's a continuous restriction here. It does have to be a functor that honors continuous. I think that means basically it honors limits. Here it has to map, I think it may have to map colimits in C. In other words, limits in C op into limits in D. Here it was limit honoring, maps limits to limits. In that case, we can map between persistence and cumulative narratives. This is really interesting. So look, if you have a persistent narrative like this, It's worth noting that this is a contravariant map from T into C, right? What this is mapping is each object in T goes to an object in C, right? Right? That's what that means. Each morphism in T from A to B goes to a morphism in C from B to A, right? But if you think about it, that can be written equally well this way. The same objects are mapped to the same objects here. A morphism in T from A to B will go to a morphism in C op from A to B. In other words, morphism in C from B to A. Let me say that again. A morphism in T from A to B will go to a morphism in C op from the image of A to the image of B. I should have saying that earlier. Image of A to the image of B in C op. And therefore, in C, it will go from image of B to image of A, right? Again, I should have said that. Okay. So we could, if we have this persistent narrative of this sort, we could write it just like this. We could say, if we have one of these, we might as well just write it as one of these. And then look, if we have something K going from C op to D, we could just post-compose it with this, right? We could just hit it with K. And we have something here, F. That's what's given to us. That's our persistent map for T to C. Persistent for persistent narratives, each object in T to C, I should say. Each object in T to C in this category is of T op to C. It can be written as T to C op, and then given such an object, T to C op, we can hit it with this to get something from T to D. And there we go. And something of this form is inside of cumulative narrative. So each and every object in T to C, right, and sorry, persistent narratives, any persistent narrative from T to C, there's all category of them, any one is of this form. And we can map it to a cumulative narrative by just using a functor such as this. So given a persistent error from T to C, we can map it into a cumulative narrative from T to D. And given a cumulative narrative, we could do a similar trick. A map from T to C can also be written as a map from T op to C op. You have ops on both sides. The objects map just like before. The ops are appropriately reversed on both sides. And we can, given that, we can get something by post-composing it with this, like doing this and then this, we can get a map from T op to D, which is in this. I don't think it is that, it's in that, right? It's in that category. So it's an object of this. Yeah. So I think this should say in this category or in this category. Yeah. For any of these. The category is I think called C, D, and each object. So there's an adjunction here, and adjunctions are beautiful creatures. powerful, insightful, with deep significance, tied in with notions, and many important notions, including with monads, or units, co-units, and so on. We don't have time to go into them, but they reflect deep structural similarity between two domains. And monads are, and adjunctions are associated with a certain directionality. They're associated with two functors, one going each way, one going the other, such that one domain is not the exact mirror of the other, but their structure is the same. In particular, there's this constraint involving the similarity in the Hom cells, such that going from one to the other and back is that doing the round trip is not exactly the unit functor on, for example, starting at D, going to C, and then taking the right functor back doesn't give you identity on D, but it gives you something that is related in some deep way here to the structure of the situation. So here, taking L and then taking R is related. You have a natural transformation from that, from what you get this way, the functor you get this way back to identity. And you have a natural transformation here and taking a round trip. These are called the unit and the co-unit of the monads associated with it. And this is the structural similarity. So here we have our category C on the left. Here we have our category D on the right. The left functor goes from D to C. The right functor goes from C to D. And for any C, and for any C in category C, and any D in category D, if you take the left functor from D, so again, any pair C and D, if you take in C and D category respectively, if you take the left functor from D and consider the Homs, the morphisms down to C, that's the same as they're on a one-to-one basis with, typically directly sort of reflect the morphisms going from D, your starting point, to RC, where you get to by this map. So if you take this round trip, going back from C to D, there's in this particular way, you'll find that there's this kind of mirroring going on here. So these Homs are on one-to-one basis with these Homs. And there's this natural transformation from the identity functor here, or from this, where you get, if you go like this and then like this, to identity here, and a similar one over here. So this basically reflects deep common sort of common structure, orderliness between these. There's a consistency between these two categories. And what we have here is one of these adjunctions between these two. So cumulative narratives, this is a category, cumulative narratives here. So it's like, these are all cumulative narratives over here. Excuse me, so it would be the flip. So this points to the left adjoint. The left adjoint is this guy. So this would be cumulative here. This would be persistent. each of these guys would be specific persistent narratives, specific mappings from T up to some D. This one over here. Each of these would be some particular cumulative narrative with a mapping from T to D. That structure preserving, limit preserving mapping. And there are these adjoint functors between them, going this way and this way, reflecting sort of this common structure. And one thing that this means is, given one of these here, you could turn it into one of those there. Given one of these, you could turn it into one of those, which is really powerful. So these cumulative worlds in these persistent worlds are related to one another in some systematic way. There's also, so that was another animal that comes to the watering hole here. You may remember another of these elements of fauna coming to the watering hole, the slice category. This is another thing we visited in the course of the semester, and it's good to enjoy the pleasure of its reacquaintance. So you may remember that given a category C and an object in C, a slice category, so C sliced over X, is a category. It's a derived category. It's a category that's defined by C and X. Okay. What is this category X? Well, it has objects and has morphisms. What are the objects in this slice category? They are pairs of objects in category C and morphisms in category C from C specifically to X. So for a given object, so each object from the original category C, will be in our slice category, as long as it has some morphism into this other object X. But there'll be sort of a copy of it for each object for each morphism here. So each of these C's is associated with each object in our slice category is an object from C, shown here, and a morphism into X, just like this. Here's another object in our slice category, D, and its morphism. We're showing them in this diagrammatic way because the morphisms are commuting triangles. The morphisms are like that. They're maps from this object to this object in category C that honor this commuting condition, that honor this map to X. So they have to preserve this map to X. C's relation to X has to, with this map here, has to be consistent with D's relation to X. If there's no such commuting triangle from C to D, then there'll be no morphism in the slice category from C to D. Slice category is going to have these. Now, this can seem a disconnected, sort of dry definition of uncertain significance. But what it has to do with is kind of annotating C with information, extra information, you could think of it. And we want maps between C and D which honor those annotations. So that if D is annotated with information from X and C is annotated from information X, C can only be mapped to D in ways that preserve those annotations, that yield similarly annotated things from C being mapped to similarly annotated things from D. So if something from C is annotated in a certain way from X, it can only map it to something in D annotated and inappropriate in the same way. Such that if we go like this, and then we ask about that annotation, it's the same as doing this. So a slice category preserves annotations. It may be helpful to see an example. You may recall this for graphs. I don't know if you recall this for graphs, but this is our schema for graphs, right? Ignore the J of uncertain ideology. Here's graph, right? Here's our schema for graphs. And here's a particular graph, right? It's a graph with two edges and one vertex. You recognize that? Okay, it's a graph. That's a graph. Don't get confused that this is a category. This ain't no category. This is a graph here. It happens to be encoded by this, but what I'm showing here is a graph with two edges called plus and minus and a single vertex. Okay, these arrows here are not morphisms. They're edges in a graph. Are we okay with that? So here's our graph. I think you'd agree this is a graph. This is the encoding of a graph as a C-set. And somewhere in the category of graphs is this particular one, right? And you may recall the category graphs has graphs as objects, and what are the morphisms in the category graph? Do you remember? Graph homomorphisms. They're like embeddings of this graph into that, or coarse grainings where a couple edge nodes here get sucked down and they squish down, they get glommed into several vertices here get glommed into one vertex here, but then all their edges get glommed together. Do you remember that? Okay. So like these two might they get squished down maybe into this one, right? You get mapped down and one gets mapped to three, maybe. Okay. So this might be a transformation. And it turns out that those graph homomorphisms are natural transformations. I mean, that we think of them as squishing things down, but they're really natural transformations. So I don't know if you remember, but we talked about if C is a graph and D is a graph, and we have a slice category of graphs sliced over, and we slice it over this graph, there was a question of what does that do? Like what's the effect of this? So suppose this is one graph, and this is another graph. And we have this graph here. What does this do? Can you tell me? So we have one graph here, we have one graph there. These are graph homomorphisms where we're looking at something, we're talking about the category of graphs, and we're talking about a morphism between graphs C and D in the slice category. We're depicting it this way. A morphism is a commuting square of this form. So within this category, if we have this commuting square in the category, the slice category of graphs sliced over this, there will be a morphism from C to D. So I'm asking, what is this? If this is a graph, C is a graph, D is a graph. This is our sliced over thing. What is this doing? These are graph homomorphisms. So what is it saying? So let's maybe we could draw this out, right? Okay. Maybe I will go and yeah, I'll just recreate that. So here we go. Okay. So slice graph, slice category with polarity labeled graph. Category sliced over polarity labeled graph. Okay, here we go. Put it into that background. So here we go. We're in the category graphs. Here's an object, which is going to be a graph. We're going to call it one. We're going to call it C. Here's another one, D, and here's another one, which is going to be our nice little one. So here's D, C, here's D, and here's X. And what I'm telling you is the graph that's here, these are graphs. So this is in category graph. I think I called it there GRPH, but so this is our category graph. So there's lots of graphs around in this category. You have to have this commute. Okay. In order for a morphism from C to B, D to be present in the slice category. So let's do that one again. Okay. Okay. So here's our slice category. There's graph sliced over. I'm going to draw the graph. I'm going to draw this graph with a plus and with a minus. This is our graph. This is our graph. Okay. And we're going to have the analog to C and the analog to D there. And the question is there a morphism between them? Okay, let's draw what these look like. So first of all, what are we slicing over? We're slicing over this guy and this guy. So this is our graph over which we're slicing. That's our graph. These are graph homomorphisms. Graph homomorphisms. We're trying to figure out, is there a, call this F and G, I'm going to call this H, and I'm going to be proper, I'm going to label this. Is there a morphism between these within our slice category, our slice category here, sliced over this? So the question is there a morphism? Okay, what is there a homomorphism there between graphs that honors this? Okay, so let's imagine we have a little graph. Here's a graph. We are going to have, for our graph, we're going to have a negative arrow. That's going to be one graph here. Maybe I'll draw, I should have drawn the graphs if I had presence of forethought. I would have drawn the graphs like this. In red. I should have drawn these in red. Well, okay. Okay. I don't know. I will. Okay. There we go. Okay. Okay. So there's our first graph, and we're going to draw for our second graph another graph, and we're going to draw it in red. There we go. And we're going to here have an arrow from this to this with a plus. Is there a map between them that will honor? So is there a map from this guy down to here? Okay, it's yeah, so first of all, there is a map here, right? Where both A and B go to this red, to this black dot, right? Okay. Is there a mapping from this guy down to this one? From this one down to this one? There is. Both go to the dot. Is there a mapping from this one to this one? So I'm sorry. I did something crazy. I did something crazy. I thought I labeled one with a plus. Yep. Yeah. So if I label that with plus, is there a mapping that goes? So as graphs, if we ignored the plus here, if we ignored, okay, I don't know quite how to shrink this guy. How do I, oh, okay, I somehow succeeded through unknown means. Okay. If we didn't have to worry about this, that's not what I meant to do. If we didn't have to worry about the bottom part, if all we were concerned with this as a graph homomorphism, is there a graph homomorphism from this to this? There certainly is, identity, right? Or essentially, yeah, this to this, this to this. Well, that wasn't quite artful. This edge to this to the only edge, right? Okay. So there is a map. If this is minus and this is plus, what we need is for this commuting square to, we need this to be a commuting square. So if these two map down to this and they go to minus, that this will then go to minus. We need however this maps over. So this vertex is going to have to map to some vertex here, right? One or the other. This one will have to map to one or the other. And this edge is going to have to map to an edge there. And we might think, well, okay, let's map in the way shown, right? Maybe I'll put these in a different color. Maybe I'll put these here like that. If we were to map them, and if we were to map, we might think we could map this if we didn't have to worry about polarities. So put aside polarities for a moment. Just as an edge, it could map to this edge, right? The problem is that when we map it down here, this edge has to map to this one, right? Which is different from where this edge up here mapped to. So let me see if I can show this. I'm going to try to use color in my sort of poor way. I'm gonna try to use color. So this edge here, I'm saying has got, in terms of F, it has to map down to this. I think you'd agree, right? Because maybe I will show with F. Let's make F like this, and maybe this goes to this, right? This goes to the same thing. And then the blue goes to the blue edge there. This way, if we try to do with light blue, if we have our strategy of that, if we consider them only as mappings of a normal graph, now we need to make this commute. So now we have a challenge. And in fact, it's an insurmountable challenge. Because if we go and we map, and I'm trying to think of the least bad color. Maybe green is the color. Okay. Okay, if we map this guy down, we're gonna call this whole thing green. There we go. All right. Okay. Green is going to map that vertex to that vertex. It's the only vertex it can map to, so you don't have much choice. Both map to there, right? But then the plus, what can it map to? Well, there's nothing that. So what I'm saying is that, right. Here, yeah. So maybe this is I'm going to put it this way. Let's put it in. We already have orange. I'm going to put it in magenta. Here's our magenta. Okay. Here's our magenta. And that has to map down to this. So what gives these, this is maybe the best way to put it, what gives these edges their polarity is their map down to this. That's what I'm saying. It's this orange map where it maps this edge, whether it's to plus or minus, down here, is what determines whether I call this negative or positive. The fact that it mapped to the blue, the big blue down here, right, meant that I could legitimately label this as minus because it mapped down. Orange mapped, this is a graph homomorphism. It has to map vertices to vertices, edges to edges in ways that play nicely together. And this edge, blue, big blue, mapped down to big blue here, which is negative edge. Okay. That's what I'm calling this edge. I could have called this flower, in which case I would label this flower. I could have called this elephant, and I would have labeled elephant, right? And I could have labeled this mastodon, right? And this could map down to mastodon, or indeed woolly mammoth. But it's the fact that these morphisms, these graph homomorphisms, it's the choice of where those graph homomorphisms have mapped these particular edges that give them their name. This is like, I'm going to call this, and for some of you, you'll recognize this terminology. I'm going to call this a type graph. Its purpose is to specify the types associated with the edges here. It doesn't specify any types. There's only one type for vertices. That's why there's only one. There's two types of edges. The fact that we have two edges called minus and plus means that there's two edge types up here by virtue of how they map down to this slice object. The slice object is setting the typing for these guys up here in terms of, in this case, the edges. And so do you understand that point? That these homomorphisms down to a type graph specify the typing for the edges up here because they have to map each edge down to one of the types of edges down there? Okay, that's a key point. If you understand that, then the next thing is, how do we make, if we have a map from this guy here to this guy here, how do we make that whole thing commute? Well, we have to map big blue here over on the left into something on the right that when we map it down to the type graph gives the same type as if we map big blue down directly. So whatever big blue is mapped down to directly here as its type, we have to map it over here. This fateful choice here has to map down itself for this triangle to commute by big green to the same type here, right? That's what it would mean for it to commute, that if it goes this way, it's the same as going that way, right? And when I say go that way, I mean whither this big blue is mapped, right? So what I'm saying is these enforce typing on these independently. This idea that it has to commute, that this triangle has to commute, enforces that the mapping from this to this honor that typing, that it preserves that typing, that it maps like to like, that birds of a feather flock together, that minuses are mapped to minuses. So the fact that we can't map big blue to plus is a feature of this situation. Now, I would note that like in this case, there is no morphism. There exists no morphism that will make this commute. Yeah. And so this does not exist in the slice category. Now, there might be some other, if we elaborated this, if we had a minus arrow over here, if we had a minus arrow over here, then there would be a mapping to the minus arrow, right? Like here, maybe I'll do that just to make it more obvious. If we had a minus arrow here to minus, and that were mapped down to by green, by big green to, okay, now I've unartfully chosen the path. So maybe I'll do it around here. That were mapped down to here. Then we would have this possibility of mapping this guy over to blue to this one, because that one maps down to this. In which case, that mapping does exist over in the slice category because we have this commuting triangle. Do you see what I'm saying? Okay, so I'm gonna there. Maybe that goes a bit too tall. There. Okay. Are we okay with this? So what's going on, to bring this back to the paper, is that they make the point that you could use this typing type of trick. So this is a deep thing, what I'm showing you with slice categories. This is one of the nicest tools in the toolbox for C-Sets to be able to encode this. It's really slick. It's easy to do. You can declare slice categories, etc. CatLab has some support for slice categories, I think. So it's this general idea of being able to impose typing. And I think you should recognize, probably you'll recognize here, that same trick could be used with graphs to label edges by integers, right? To characterize like the latency of an edge, how long an edge in a graph is to live. Mhm. For that matter, you could have them labeled. So what I'm showing here is, again, a graph. I'm showing it in this diagram, but the idea is it's just a graph. And this is a graph. And the map from this graph down to here will essentially label edges by their latency. And any map from C to D of graphs will need to map an edge here in this graph C into a like labeled edge in D. That's right. That's right. And such that this triangle will commute. And what they argue here is that by encoding these structures as C-sets, these graphs as C-sets, we have all this extra flexibility that we can build up very sophisticated structure to characterize things like temporal graphs. But more than that, we can enforce consistency. So, for example, we could have typing system for vertices. That says no typing for vertices. Our example had no typing for vertices in this graph, right? But we could have, like, we could have added some distinction between vertices that are, I don't know, that are agreed to by all participants versus only a subset of participants, or vertices where we have data and those where we don't, or something. Here, what they're arguing is we could have, for vertices, we could label vertices by numbers. And by having this mapping, we would need to map things here to things here that are to vertices with the same, that agree in terms of their numbering. And what they say in the paper, observed in the paper, is that by virtue of doing this is in, it's in this section here. This is this paragraph, right? So they're talking about this single vertex graph, and where the edges, there's edges in 1-to-1, for each natural number. So it should have had 0, and so on. And then consider the slice category. So these would be, this is the schema for graphs. So these would be graphs sliced over this. So it's like graphs sliced over this. We're considering that. And what that allows us to do is to capture assigning natural numbers to each edge. And we can similarly label vertices and edges. And basically, we can capture encoding of time in the graphs, what times they appear and what times they don't appear. So when we compute the sheaf, we can record, for example, when an edge appeared, perhaps, or when it disappeared, or something like that is perhaps what they're thinking. A key thing is that they observe about a definition in the literature is that this definition specifies for edges whether an edge exists at a given time. Mm-hmm. For a vertex, whether it exists at a given time. Mm-hmm. And it allows us to say for a given edge, for a given period of time, I think how much longer it will live, or something like that. For a given graph, vertex, how much longer it will live. This is someone's proposal from the literature, these folks. And what they're observing is that there's no consistency relation. There's no commuting condition. There's nothing that says that this has to agree with this, which could mean, an edge lasts longer than its vertices, which doesn't make sense, for example. Or that one of its vertices disappears before it and the other before it does and the other disappears at the time that it does. Two vertices associated with the edge disappear at different times. And the edge is hanging. It also doesn't enforce that the time remaining reflects this time. And what they're arguing is that if we encode things categorically as C-sets, we can enforce those coherence conditions. We can require things like commuting conditions that enforce that things play nicely together. They further note that by encoding C-sets, you can encode many other sorts of graphs. So this is a reflexive graph. It's a traditional, this is a reflexive graph. This is a involution graph. So this is a undirected graph. So all edges are bidirectional. This is a reflexive and bidirectional graph or undirected graph. This is a mumble. I don't know what this is. It's a half edge. It's a half edge. So I guess mumble. I guess that means not every edge. Yes, not every edge has to have a source and target. So you can have half edges. There could be, and each, I think something along those lines. Anyway, but each half edge has its involution. And they note that you can encode Petri nets. And they have this nice description about beyond encoded graphs, beyond encoded sets. We could encode, for example, metric spaces. So we can have captured the locations of ice cream outlets in Venice, ice cream companies in Venice, which is a rather pleasing prospect. And we could have that data captured in a C-set. I would note we could also capture in a simplicial set, simplicial complex at different points of time. And they're arguing that this has really nice properties because we can enforce consistency. Okay. I think that's all we have time for today. I did have, I'll post these slides. Next time we'll be finishing this paper. So section 2.5, which talks about lifting static concepts to automatically to temporal concept. So if you have a static concept like that of a path or a clique, you can apply what you normally apply to a single graph. You can apply it to a temporal sequence of graphs and a whole temporal narrative, be it cumulative or persistent, and talk about cliques that persist, paths that persist, paths that are present across a time sequence in a cumulative sense or in a persistent sense, which is rather powerful. And there's going to be some deep relationship between these, which is quite interesting. You could change the resolution of analogs. This is really interesting. So you summarize not only by weeks, but instead you do it by months, or days compared to by months. So you can go for different temporal categories and have this structured transform between the picture you get on a per day basis for persistence, on a per day basis for cumulative, compared to what you get on a per week basis for those, or a per month basis for those. And then they talk about towards a general theory of data, note the potential for linking it in with dynamical systems perspectives, which is of core interest to our work. Okay, so that's all we have time for today. I think this, maybe it's obvious, I think this is an extraordinary article. I also think it's an extraordinarily important article for us. And I appreciate your consistency, your persistence with it, and your accumulation of knowledge with it too. I think we'll stop now. I have to talk with Nastaran in a graduate meeting, and we will finish this paper on Monday. And then in the final two lectures, we'll be discussing Robinson's paper. Oh, one other final thing. This is actually reasonably important. It's an administrative matter. I'm away for the Canadian Mathematical Society conference where Cheyenne and I are presenting an intro to CATLab a week from today in Toronto. What that means is we can't hold it at this class at this time, because at this time we'll be teaching in Toronto. I'm seeking to arrange another time we can meet. My original